Hey everyone, welcome back to Workshop Quick Takes. Today I'm going to do more of what I do best, and that's waste time on a lost cause. Today's lost cause is this Coleman camping lantern I found up in the mountains. It has some physical wear and tear on it. I don't know what its history is. I found it without batteries. When I got into it, I discovered there was a fair bit of corrosion on some of the battery terminals in here. Now I've since taken those apart and cleaned them up, and it should work, but I haven't tried it yet because I just now got the D batteries I need. But let's go ahead and put the multimeter across the light bulb circuit just to see if anything comes on. Getting nothing. Not sure which one is on and off. Still getting nothing. So I'm betting it doesn't. We'll pop the top off and take a look at the bulb directly. But for now, I'm going to go ahead and pull these batteries off and see if I can get... looks like they're all in series, so it should be 6 volts that appears up at the top where the light bulb circuit is. And one of the things I was thinking about with this, which is part of why I describe it as a lost cause, is this is an incandescent bulb lamp. So what if I converted it to LED? Well, that's a complete waste of time because you can get a LED camping lantern about like this over at Harbor Freight for, I don't know, 22 bucks. But I've got enough parts and pieces to do it from materials mostly on hand, so... Call it a hobby. What I do like about this design in particular, if I can get it to work, is the fact that it has these D cells down here. A lot of the newer LED lanterns, due to the lower current draw, they like to use AA's, and that's fine, but AA's just don't have the kick to stay illuminated for a long period of time. So as expected, still nothing. Let's take a look at what we got up here. I've got these 2 terminals where it's where the power comes up. If my battery tray is working, I should be seeing about 6 volts DC between these 2 points. So let's go find the 20 volt scale on this particular meter, positive and negative. 6.47 volts, so that part's working. So it sounds like at this point I've got either a problem with the light bulb or a problem with the switch. Let's take a look at these 2 terminals here. Right now it's open, so I'm not expecting to see any continuity across there. Now that I can see actually closes the terminals in there. I don't know if you picked that up on camera or not, but yeah, open, closed, open, closed. That's how that switch works. Well, that says I've got light. So it must be something between the connection of the terminals here that's causing my issues. Maybe, if I pop these up a little bit, I took some tension off them when I reassembled this thing after doing the battery terminal cleaning, so I'm not sure what condition they're actually in at the moment. Okay. The way this one works is there is a 5th oblong tab slot right there that goes into. So in order to actually line this thing up, I have to do that and then twist a lock. There you go. So we know the basic hardware works at this point. That's a good sign because it means if I start disassembling the top here and trying to fit some more circuitry in, I should be able to do an LED conversion fairly easily. One hindrance to this is that I could try and drive at 6 volts directly, and maybe I will. I've got, what have I got over here? I've still got quite a number of these Harbor Freight puck lights that I could pull the cob LED panels out of and convert those into some sort of element in there. And if I took, what are these? I think these direct drive at 4.5 volts. So if I took 4 of these and did 2 series parallel pairs, I think I'd get a decent amount of LED light out of there. Another option is this old H3 style LED light that I originally bought for car use at some point. However, this along with this garden light, both of which I know this one here should work reasonably well, and this one here should be pretty reliable. I've been using several of these as substitute dome lights in my 2000 Jeep Cherokee. But I need 12 volts and I've got a 6 volt source, so what am I going to do about that? Well, I'd probably have to step it up somehow. This is a Chinese source boost converter. You can buy these all day long off of eBay in different formats. The adjustment screw is here. There's also a buck version that'll cut voltage instead of boosting voltage. It looks very similar but has a slightly different chip. And there's others even that are postage stamp size. I mean, they occupy literally this much board from here to the screwdriver to the end and have a very, very tiny adjustment screw. And there are still others that have USB power input. I mean, you could even get one of these with a connection for a LiPo battery pack, and then you could have a rechargeable unit that's USB rechargeable and runs off battery. Okay, before continuing further, let's get some numbers put on this. Let's start by using this DC power supply and powering just this light bulb and find out how much current it's actually drawing off the batteries when it operates. And then that'll give us a baseline to tell us how our LED solution is going to improve battery life or not. So those 4 batteries, when they're fully charged, they output about 6.47 volts, but let's just go with 6 volts. So I'm going to turn on the output, switch to the plus 25 volt rail that I'm using here. and just start that at about 6 volts. See if we get this to light up. It do. Now according to that there, 789 milliamps roughly. A little under 800 milliamps being pulled by this light bulb under normal operation. And of course then that falls off as the battery voltage falls off. The lamp operates dimmer and dimmer as it goes. Okay, so actually let's just think about that a minute. That's 800 milliamps or 0.8 amps at 6 volts. Yeah, let's just run the numbers so we can actually see it. 0.8 times 6, yeah, 4.8 watts. So almost 5 watts to get that much light out of that bulb. That's actually a pretty impressive current draw for 4D batteries, all things considered, and it'll last a while, but maybe the LED solution can do better. Let's find out. So let's just start with this lamp here, and let's run it up to its full voltage and see what it does. Now I have a hunch that there's a voltage regulator in here, but I don't know for sure. Let's check the behavior and see what it looks like. So I'm going to start at 6 volts down here, and I'm just barely getting some illumination off that. 7, now it's actually coming on. 8, 9, 10. Something interesting is happening here actually. Once I cross the threshold from about 8 volts, right now I'm at 103 milliamps. I go to 9 volts, it jumps to 126. But then I go to 10 volts and it starts to fall back off again as we approach full brightness. 111, 101 at 11 volts, 93 at 12 volts, and 87 at 13 volts. And when I get to 14, which is just over the 13.8 the car alternator operates at nominally, now we're at 81 milliamps. If I go higher, 15, 16, it keeps falling off. So it appears there's a regulator in there that's maintaining a constant current across those LEDs. It's not just connected in series and hope for the best. So that's interesting to see. But let's take a look right there. Let's say right around the 11 volt range. I think that's probably an ideal place to operate it, that it won't overburden it. And it's exactly 100 milliamps. So what does that work out to? 0.1 times 11, 1.1 watts. Okay, so now let's connect it through the boost regulator here and see what that does. So we're going to go back down to 6 volts to start with here. And I'm going to shut off the output there for a moment. So what we'll need the boost regulator for if we continue down this road is to take 6 volts from the battery and boost it up to the 12 volts that the regulator in there is designed for. It's not the most elegant solution. It'd be better to find a bulb that operates at 6 volts directly. But because automotive applications are really popular and some low voltage garden lighting systems also use 12 volts, you can get 12 volt lamps all day long. And the best solution probably is to power a 12 volt lamp from a 6 volt supply. Okay, so now what I've done is I've switched colors just so I can keep track of the difference between the high side and the low side of the regulator here. I'm using white for positive and green for negative. And I've got a multimeter here. Let's pull that into view and just see what the voltage is looking like on the output side of the multimeter. Turn the voltage back on. I've got 6 volts coming out here, and I'm seeing 11 volts over here. Now let's see if it still holds that when I get the light on it. White is positive. Okay, our light's back. Dropped very slightly. Now note what's happening here. This is pretty much what we'd expect. We've got 212 milliamps at 6 volts. So before, with just the light connected straight to a 12 volt supply, we worked out that we were drawing 1.2 watts. 0.21 times 6. 1.26 watts. So I would expect that the difference of 0.06 watt is losses in here, but that's not a lot. And at the moment, I'm operating this way below its capacity. It's just maybe a slight bit warm. Now just for fun, let's watch what happens if we adjust this output screw. And we're still getting the same behavior, almost exactly 0.206, because again, we're lowering the voltage coming out of here, and this is adjusting up to compensate. So this is looking like a viable solution. Now the question is, do I want to use this light, or do I want to try something else? Let's take a look at this here. This claims to be a 2 watt bulb. Let's find out if that's true. We'll do it to both 12 volts and then through the regulator at 6, and see how it performs relative to that one. That there, you can see it has 2, 4, 6, 8 LED packages. I don't know how many LEDs are in each of those packages, but then there's also a fairly healthy looking voltage regulator down below there. And my experience with this design so far, using it as a dome light, I haven't had any issues with these at all, unlike some of the early ones I tried out from Home Depot. So, unfortunately, the price of these also reflected that. I happened to get this one on clearance for about $6, so I was willing to give it a try for this project. I'm trying not to spend a fortune on this. I want to work with mostly parts on hand, but this was a worthwhile try. And it's also got a non-polarized connection down here, so I can connect positive and negative to either pin, and the regulator automatically figures it out and goes for it. Didn't realize I had such a nasty reflection off of the meter there. Okay, so let's just see how much voltage it actually takes to kick on this regulator here. I'm curious, I haven't tried yet. Output on, 5 volts, nothing. 6 volts, nothing. 7 volts, nothing. 8 volts. Okay, so this one kicks on right around 8 dimly, and at 9, pretty close to full brightness, I think. 10, oh, even better, 11, 12. Okay, so 10 to 14 volts looks to be the butter zone for this one here. All right, now look at the power consumption on that. I'm seeing Again, we are seeing characteristic of a regulator here. As the voltage goes up or down around that sweet spot, then the current changes to compensate. So at 11 volts, 158 milliamps. So 0.158 times 11, 1.74. Let's try it at the actual 12 volt nominal. At 12 volts, it's 145, so 0.145. Yeah, 1.74. So it says it's a 2-watt bulb. It's actually burning about 1 3/4. But this one here has a nice, more natural light color compared to the bright white from this one, and that fact I do like a little better. So let's see what happens if we run it through the regulator. Will it behave itself? Power on. Oh, well, that's interesting. The change in current must have affected the performance of the regulator, because now I'm at 3.73 volts over here. Glad I turned that down, and yet this has already jumped to 13. So let's go ahead and dial that back down. I want to get way lower. Okay, so now we're at 6 volts on the power supply. Let's dial this up to 11. Where we were. Okay, 11 volts, and just as expected before, we've nearly doubled our current consumption. We are at 326 milliamps roughly. Now here's the other test I want to do. See, what happens is, as these batteries in here go dead, the voltage they output is going to drop. They started a little like 1.55 to 1.6 volts when they're brand new, and they'll usually be completely dead and not doing much for you, somewhere around 1.2 to 1.1 volts, regardless of what you try to connect. So in this case, what happens at, say, 4 batteries at 1.1 volts would be only 4.4 volts. So let's suppose I drop this from 6 down to 4.4. Where does the output fall off from my regulator? 5, still going strong. 4, still going strong. 3, now we're not so healthy, but that's well within the acceptable margin, assuming that the changing internal resistance of the battery as it discharges doesn't mess with things. I'm hoping not. What this is telling me is that I can run those batteries dead flat and get almost constant light output from this until just before it goes dead. So I think I'm ready to make my decision. I want to try and use this bulb. I'm going to modify that so it somehow holds it, and then I need to figure out a place to tuck this regulator in, and I think I might have one. Okay, so far here it looks like we're pretty good, but let's do one final check and just make sure that the electrical components of this will work together. There's no reason why they shouldn't, but it never hurts to find out. And do a quick tap check. Hey, look at that. Got everything connected correctly. So now, if I lower that down into there, that should make for a nice bright camping lantern. We'll need to get on modifying this next. That's going to take some careful thought. The one thing that's easy, of course, is removing the old bulb. It just twists around until this little triangle position is reached and then pops out. One thing I could do, of course, is disassemble this bulb base and figure out then how to try and remount this on there, and that's not a bad idea. But at the same time, I can't actually reuse the mounting tabs in here. I'm going to have to cut into this circuit here. The other thing too is, where is this going to mount? And I think if I take this out temporarily so that I can tuck it down in here, that trim pocket's in the way, but I think if I dropped it all the way down in here and then got it worked out so that the trim pot would drop past, this would sit pretty much in the bottom of that thing there and not interfere with this reinserting into there. Oh, that is a perfect fit. Okay, just take a quick look at this so you can see how this is just pure luck that it fits so neatly. But after taking that little piece out right there, messy, I know, I can drop that in there. And I think I'll actually keep it in there using just like a white acrylic adhesive or caulk or something that I can just glue down in there and then drop that in once I've got all the wires connected to it. And if I remove this plastic piece here, I still have access to the screw, so adjusting the output voltage, if that ever becomes a problem, won't be an issue. And as long as I don't goop it in there too hard, it should still have decent heat dissipation, although from earlier tests, it didn't even seem like it was getting all that warm. I got some wires to work with. I've got some fairly fine gauge wires here. Again, we're only dealing with about, about 220 milliamps. I think what I need to do next is I need to keep these two plastic rivets in place in order to hold these tabs firmly so that they don't start popping out or rotating. But what I can do is rotate this one out and maybe push this one down and try and figure out a way to solder into it. And then I'll have to take off some of this top plastic and figure out what it's going to be to mount this in here. I mean, maybe I'll just figure out a way to tape it in there really securely. I don't know, but let's find out. I want to keep a supply of 1/16 bit drill bits on hand because I break these left and right. One thing I do want to do just by convention is make sure that the switched side, which is this inner tab, is the one that is carrying positive. Okay, off camera I took time with a sharp knife to mod this. Before I go further with the bulb, I do need to get some wires put on it, and here's how I'm going to do that. I have these wires with this real soft insulation jacket that came off of another device. So what I'm going to do is trim that back a bit, and then push the bulb into the insulation sleeve. It's kind of like that. And leave just enough tail at the top here that I can do a quick solder tack. Make sure I don't have any wires going where they should not. Again, this is a bipolar connection. Red and black doesn't matter. I just chose an orientation and went with it. Now I need to make the final install into here. Okay, let's take a close look at the work we just did. There's the lamp secured in there. There's the wires, the orange and the black, come from the two metal tabs. Still not 100% sure how well that solder bonded, but I hope it works. And then red and black from the output side, positive and negative, return to the light up there. Now if all goes well, I should be able to put this back together and it works. But before I glue this down in permanently, let's go ahead and just partially reassemble this and see if it turns on the way we expect it to. Actually, there's one thing I forgot to check. When this installs, which way do positive and negative actually end up in there? That would be a good thing to look into. When I do this, and then twist a lock like this, is my positive ending up on my switch? Oh, lucky day it is. Cross my fingers that I did this right so I don't blow up that regulator. We have a viable lantern. There we go. There is a positive and a negative that must be obeyed up here in case someone messes with this in the future. Perfect. There we go. One last thing that needs to be marked coming up in here is that this side must always remain positive. That, of course, won't prevent somebody from taking it apart in the future, but given that the LED bulb hopefully won't have any serious failures, there shouldn't be any reason for anyone to take this apart ever again except to swap batteries. There we go. Play with it. It turned into something. I don't know how useful that'll be in the long run, but obviously the whole point of this was for the hobby experience, and in that, we have a success. Hey everyone, thanks for joining me again today. This has been Workshop Quick Takes. I started out by calling this a lost cause, but as we saw, there are things you can do with old technology that makes it behave just as well or even better than new technology. I say better because this uses D cells. You needed D cells in the olden days to support a high output incandescent light bulb for any length of time, and newer lanterns, when they have LED technology in them, they often use AA's, and sometimes they use it even when it doesn't make sense. Take this wonderful Harbor Freight flashlight, for example, 1500 lumens of output, incredibly bright. But the one thing I do not like about it is that the batteries, when they go dead, and they go dead pretty quickly if you're running it at full output, you gotta buy an entire package of AA's just to get this thing going again. But chemical batteries have an interesting characteristic in that the lower the current draw you apply to them, the disproportionately longer life you get out of them. D cells, for example, if you look on Wikipedia where they try to summarize several manufacturers' product data, output anywhere from 10 to 18,000 milliamp hours depending on load. If your load is really low, you can get the higher end of that. If your load is fairly high, you get the lower end. This originally was drawing almost 800 milliamps with an incandescent bulb. It's now drawing 350. So instead of maybe 9 to 10,000 milliamp hours that we would have gotten out of the D cell batteries with the original bulb, we might get more like 12 to 13,000. So not only do we get more light output from the LED, we get a disproportionately longer life because the lower current draw treats the battery chemistry more gently. The other thing I like about using one of these, I was able to do this using a warm white lamp, and a lot of the camping lanterns, especially the cheaper ones that you can buy off the shelf these days, use cool white LEDs for reasons I do not understand. Because if I'm ever outdoors in a situation where I need a lantern, there's chances are I'm trying to set up my meal here, there's a nice little fire going over there, we're going to roast the hot dogs or whatever, and I don't want a nice warm pleasing light coming from the fire over there and a harsh factory floor hospital grade blue-white light shining on my picnic table over here. I just like it better. In any case, I hope that gave you some ideas from your projects, and we will see you next time, whenever that is. Has anyone seen my phone?